Hey, it's Nathan, and today I'm going to go ahead and refresh one of my older videos. So I went ahead and asked a while ago at the beginning of the summer when I thought I would have time, whether or not people wanted me to remake some of these older videos that were, one, without microphone, two, on a very, very dimly lit board, and three, before I wrote everything in caps lock. And people mostly said that they wanted me to do that, or would be okay with me doing that. So this is the first one of those. We're going to go ahead and revisit Zorn's Lemma and the Well-Ordering Theorem and Undefinability in this video. So I'm going to go ahead and talk about this stuff in the video today. In general, it's nice to be able to order things, and the Well-Ordering Theorem and Zorn's Lemma in a way give us a guarantee that we can do that for any given set, but there is some weirdness that arises from accepting that these two things are true. Partial orderings are going to be our gateway for understanding these two mathematical ideas, but before we get there, I think a notion of a relation that people are probably more comfortable with and will let me naturally talk about orderings is that of equality. So I'm going to go ahead and start there. So in mathematics, there are several different types of equality, and in general, these relations have three properties. One, they are reflexive, so everything is related to itself. Two, they are symmetric, so if A is related to B, then B is related to A. And lastly, they are transitive, so if A is related to B and B is related to C, then A is related to C. There are, again, several examples of equivalence relations and notions of equality throughout mathematics. But probably one of the more accessible, non-trivial ones is that of parity of integers. So parity, or equivalence module 2, breaks up the integers into even and odd numbers, where all of the even numbers are related to each other and all of the odd numbers are related to each other. So under equivalence modulo 2, 2 is equivalent mod 2 to 1008, which is equivalent mod 2 to 0. And on the other side of that coin, for odd numbers, right, 1 is equivalent mod 2 to, let's say, 151, which is going to be equivalent mod 2 to 27. And so in some sense, you can go ahead and think about equivalence relations taking a set and breaking it up into chunks that are pairwise disjoint or separate from each other. Partial orderings, on the other hand, are very similar to equivalence relations, except they take one of the main properties of equivalence and just turn it on its head. So, whereas an equivalence relation is symmetric, a partial ordering will be anti-symmetric, which means that if two elements appear as if they have a symmetry between them, that being that, like, say, A is less than or equal to B and B is less than or equal to A, and with respect to the ordering, then anti-symmetry says that those two things that look like they're different are actually just the same thing in disguise. So the partial ordering that you're probably the most used to are the greater than or equal to or the less than or equal to partial orders on some set of numbers. On this small set of numbers, you can see that if we write out all of the possible relations that are present on those numbers given the less than or equal to ordering, you can see that all of these numbers fall in line with one another. And this is what is meant by a total ordering. So a total ordering is just where you can take any two things from your set and you can compare them in some way. So much how equivalence relations can be used to visualize a set as being cut up into distinct chunks, a partial ordering can be used in a similar way to visualize a set as a tree. So in our small example, the tree diagram is just a straight line. But in general, the tree that you generate with your partial ordering can be quite complicated. This diagram that is derived from an ordering is called a Hasse diagram. And so in a Hasse diagram, each node is going to be an element of the set granted by anti-symmetry, because you can't have two things occupying the same space in the ordering by anti-symmetry. And then the arrows between those nodes are going to represent how elements relate to each other. Note that in a Hasse diagram, you can only have arrows going one direction, because if you had them going both directions, we would run into an issue again with anti-symmetry, and you would have to collapse that bidirectional thing into one node because they would have to be equal things. So to get in a small example that looks somewhat like this crazy general case of a Hasse diagram, we can actually look at a power set of a small set of elements. In this example, we're going to go ahead and just look at a set of 3 elements. Then the power set is going to be the set of all subsets of that set of 3 elements. And so we'll get these 8 elements in our power set. The subset relation is a partial order on sets. And so we can use that subset relationship to generate the following Hasse diagram. If we look at every path that obeys the direction of edges, we have a totally ordered subset of our set, otherwise known as a chain. So for example, if we go ahead and start, the empty set is a subset of the set containing C, which is a subset of the set containing A and C, which is a subset of the entire set X. And so the set of the empty set, the set of A and C, and the entire set X is a totally ordered subset of the power set of X. Notice that there's actually more than one chain in the Hasse diagram. So it follows that not everything is comparable. So for instance, if you go ahead and look at the set of A and the set of B, there's no path between them that obeys the direction of edges. And so the set of A and the set of B are not comparable with respect to the subset relationship. This small example also shows us that the subset relationship is not a total ordering. That meaning that there is not a way to always compare 2 sets in terms of the subset relationship. So another thing to mention here before we move on to more stuff is that generally speaking, when you have a set and a partial order on that set, you have something called a poset. That's what it's called in a lot of different places. If you go out and look for more stuff on this online or in papers, usually they'll introduce partial orderings and then they'll call sets with partial orders on them posets. So I'm going to start talking about partially ordered sets as posets from here on in. Also, another thing that you might want to look into when thinking about this stuff is if the Hasse diagram actually conveys all the information of a partial ordering. Now, this isn't a terrible exercise. It's more just an exercise in being able to reconcile a definition in words with the picture that I propose to give for this thing, which does in fact work, but it's something that also can be checked. So if you're not having a great time connecting partial orders and Hasse diagrams at this point in the video, this would be a good place to stop and think about that, because some of those ideas are going to be important as we move into talking about Zorn's lemma, which is the next thing on the docket. Now that we're a bit comfortable with orderings, we can go ahead and begin talking about Zorn's lemma, which can be stated as follows. Let P be a poset such that every chain in P has an upper bound in P. Then the set P contains at least one maximal element. Here, maximal means that there is nothing larger in the sense of the ordering imposed on P. So at least at this point, if you've understood everything so far, the statement of Zorn's lemma should be relatively accessible. However, in order to start talking about some reasoning behind why we might believe Zorn's lemma to be true, and I'm being intentionally vague with language here because it'll be important later on, we need to actually talk about ordinals briefly, not in depth, but just briefly we need to talk about ordinals. So the ordinals are a mathematical generalization of the natural numbers. You have 1, 2, 3, and so forth, all the way up to omega, which is the symbol used to denote the first infinite ordinal. And then you have omega plus 1, omega plus 2, omega plus 3, and so forth until you get to omega times 2. And this process can continue for as long as you want it to. In particular, the ordinals are well ordered, meaning that there is a least element for every collection of ordinals that you consider. Also, there is an ordinal for every possible size of a set. So the collection of ordinals are too big to form a set themselves, and are thus a proper class. These two ideas about ordinals give us enough mental leeway in order to go ahead and sketch an idea of why one might believe that Zorn's lemma is true. In particular, we proceed by contradiction. So suppose that we're given some poset P, and there is a chain in P, call it C, where we have an upper bound of that chain that lives in P. And then suppose that P is a poset without a maximal element. So if you had the empty set, for the sake of argument, all of these statements that we're talking about would be trivially true, or rather vacuously true. And so we want to avoid that. So we do have a non-empty poset to start with. So there is an element in there somewhere, and we can start the Hasse diagram, or at least our visualization of the Hasse diagram, on that particular element. So go ahead, look at that one element, and notice that that element by itself forms a chain. That is, it is a totally ordered subset of the poset P. So by our supposition, we should be able to find a second element in our partially ordered subset. And so the reason that we keep finding more new elements is because if we couldn't find a new element, or the upper bound was in the chain, then we would have a maximal element, which is something that we're supposing does not exist in P. So that's why we always need to find a new thing. But there's a problem here. So since we can form a new chain by taking the old chain all the way up to and including the upper bound of that chain, then we should be able to find another upper bound and continue to find bigger and bigger elements forever. And these elements are going to be well ordered. So there are going to be the same number of them as there are ordinals, because this process never ends. This is what gets us to a contradiction in our logic, because the ordinals are too big to be contained in a set, yet you found a chain that is essentially a copy of the ordinals in your set P. And so then that would say that the ordinals can fall into a set. And so we have an issue there. So P would be too big to be a set, and that would give us a contradiction, and that would imply that Zorn's lemma would be true. Huzzah. So between ordinals and orderings, there's a lot of, probably like foundational is the word for it, but highly structured things that are operating in order to get this argument for why Zorn's lemma may be true. And I'm being vague with my language here because Zorn's lemma is equivalent to the axiom of choice. So essentially, Zorn's lemma is true if you accept that choice is an appropriate axiom or not. Some mathematicians in certain fields do not think choice is a fair axiom. Others in other fields of mathematics don't really care and just use choice because why not? So along with being equivalent to the axiom of choice, Zorn's lemma can also be shown to be equivalent to the Well-Ordering Theorem. And so the Well-Ordering Theorem says that no matter what set you give someone, they should be able to put a well-ordering on that set. So a natural thing to ask is, well, what about the real numbers? People use the real numbers a lot. Can we put a well order on the real numbers? The natural thing to try then would be to go to, hopefully, the natural choice would be something that we're all familiar with as well, which would be less than or equal to. But there's a problem there, because even though less than or equal to is a total ordering on the real numbers, it's not a well ordering, because if you look at subsets of the real numbers that are open intervals, like an open interval from, say, A to B, where A is less than B, then you have an issue because there's no least element in that open interval. You can always find something smaller and smaller and smaller and smaller. So less than or equal to doesn't work as the well order on the real numbers. And in fact, the anticlimactic punchline is that there's actually no way to do it. It's been shown that the well ordering that you are guaranteed to have for R is not definable in a set theoretic context. So yeah, the existence of one of these undefinable but true statements within this axiomatic system that I am currently using for this video, which is to assume that choice holds, should feel a little bit off. That being said, there are many theorems that people have proven using choice and that are important to their fields. But aside from that, this is also one of those things that's brought up as an argument to use other axiomatic systems, like that of countable choice or the axiom of determinacy in place of the axiom of choice when you're doing your particular mathematical logic. But yeah, that's essentially it for this video. I really just wanted to update the quality of this video because with what I know and how I know to do things now, it just kind of makes me cringe. So hopefully I did a better job at communicating that information and also had better visuals in this video than in the old video. If you enjoy me giving my chalk stuff on the internet, you can give this video a thumbs up and you can subscribe for more math stuff like this. I've also got some PhD update stuff out there. I've got one coming out in a week or two that I'm working on currently. So if you're interested in how I am as a human, that's also on my channel too. But yeah, like and subscribe, comment, do all the things. As always, I am Nathan. This one was chalk and an updated chalk video. And I will see you next time.